Hi everyone, my name is Shruti and I'm going to be presenting our paper Can we break free from strong data augmentations in self-supervised learning? This is a joint work with Baram Zunus and Elaha Arani. Deep neural networks have proven to be highly effective in encoding complex data patterns. These representations improve generalization performance across various tasks such as classification, detection, and segmentation. However, these networks require large amounts of labeled data, which is costly and time consuming to annotate manually. Self-supervised learning has emerged as a promising solution, allowing the learning of useful representations without manual annotations. The goal of SSL is to develop high-level representations that enhance efficiency and versatility for downstream tasks. There have been several approaches to self-supervised learning methods. Pretext-based methods involve tasks such as predicting rotations to learn representations. Contrastive-based methods aim to maximize the similarity between different views of the same image while minimizing the views of different images. This is seen in SimCLR and MoCo methods. Architectural methods avoid collapse without negative samples by using asymmetric architectures, as seen in BYOL and SimCM. Feature decorrelation methods focus on decorrelating features to ensure diverse representations, exemplified by Barlow twins method. All SSL techniques we observe that currently require many strong augmentations. This can act as a double-edged sword because while strong augmentations enforce multiple invariances, they can also introduce artificial patterns and biases into the data. Our work explores the impact of these augmentations and seeks to find alternatives to reduce the reliance on them. Our research aims to answer two main questions. How do these intense augmentations affect the correlations in SSL representations? Can any kind of prior knowledge enhance the effectiveness of these methods without the use of these strong augmentations? So our primary goal is to reduce reliance on these strong augmentations, and we would like to explore different kinds of prior knowledge and cognitive biases to enhance the representations. In our work, we use our method on three types of SSL methods: the contrastive-based SSL methods, the asymmetric network-based SSL, and the feature decorrelation-based methods. We aim to integrate prior knowledge to reduce reliance of SSL techniques on strong augmentations. We take inspiration from the human brain and inspired by the cognitive process where humans rely more on shape rather than textural information, we introduce shape as an inductive bias and an additional knowledge to help the learning process. This approach aims to improve model generalization by incorporating high-level abstractions into the training process. Thereby, we introduce SSL prior, where we're inducing shape as a prior knowledge into different SSL techniques. The components of this methodology include an SSL module that utilizes any chosen SSL method, for example, SimCLR or SimCM and BIC-reg. We have a prior network that extracts this shape or semantic information as an additional view and supervises the SSL training. And we have a loss objective that ensures consistency between the SSL module and the prior network. Here we present our results. The table shows the performance of the three SSL baselines and their SSL prior counterparts for 4 different datasets. Along with IID, we also test the capability on distribution shift by evaluating the models on out-of-distribution data. As shown, SSL prior demonstrates strong performance across all the datasets. Object detection is a common downstream task and involves the classification and localization of objects in a scene and has widespread applications. The mean average precision is reported on VOC and COCO datasets. As shown, our alternative training approach to SSL not only improves the performance in distribution but also demonstrates significant improvement in challenging downstream tasks like object detection. Deep neural networks often rely on shortcuts or spurious correlations within the data, which may not really translate to the unseen data and downstream tasks. Hence, we also perform a shortcut learning analysis. Here, the figure clearly demonstrates that SSL techniques rely heavily on spurious correlations or the unintended features such as the tint in tinted STL10 dataset and hair color in skewed celeb dataset. And from the figure, we can see that SSL methods trained with the prior knowledge are less prone to learning these kind of unintended cues or shortcuts, thus mitigating shortcut learning. Deep neural networks are vulnerable to adversarial attacks. Here, we perform an adversarial robustness analysis where we have PGD attacks of varying strengths and we show the results in the graph. The figure shows that SSL methods trained with priors are considerably more robust against adversarial attacks of different perturbation strengths. In this figure, we show three different analyses, namely texture bias, robustness against natural corruptions, and performance when there is data scarcity. From the first figure, we can see that the added shape awareness in our method guides the model to learn the global structures instead of just relying on the local textural information, thus mitigating texture bias. In the second figure, SSL prior exhibits great resistance to all categories of natural corruptions, namely blurring effects, digital, noise, and weather conditions. And from the third figure, we can see that our method can be advantageous in scenarios where labeled data is very scarce. In conclusion, the SSL prior approach represents a transformative method that incorporates prior knowledge to reduce reliance on extensive data augmentations. The key outcomes include improvements in generalization, reduction of shortcut learning and texture bias, and enhanced resistance to both natural and adversarial corruptions. The future work may include exploring more ways to integrate different kinds of prior knowledge into the training mechanisms. And we hope that our work lays the foundation for improved self-supervised learning training, thus creating opportunities to develop more effective and versatile learned representations with broader applications. Thank you, everyone.